Hello everyone, today we will continue the introduction about the stress analysis in the rigid pavement. Actually, we'll finish all the rest of the contents in this topic. In previous lecture, we analyzed the stress caused by the traffic load and the temperature. Here we will continue discussion to analyze the impact of the moisture contents. The figures here shows the strain and warping effect caused by the moisture contents at the surface and bottom of the PCC slab. On top, we can see the dry warping effect, where the moisture contents on the surface is much smaller than that at the bottom, and we will observe the tension is mostly applied at the surface of the slab. While for the raining day, we can observe that the moisture contents on the surface of the slab is higher than that at the bottom, which will cause the wetting warping, and the tension is mostly applied at the bottom of the slab. The warping effect is applied to measure the impact of the moisture gradients through the thickness of the PCC slab. Usually, it's very difficult to measure the severity of the warping for the slab, and the warping effect varies seasonally, but it has some impact to the fatigue level of the rigid pavement. However, the impact is not that significant. Also, warping tends to reduce the tensile strain at the bottom of the slab, but this kind of impact can be very small. Usually for the design, we will ignore the impact of the warping due to the moisture contents. The figure here summarizes the stresses for the rigid pavement. Basically, we have three types of the stresses as we described previously. We will have the stress caused by the traffic load, the curling stress from the temperature, and the warping stress from the moisture contents. By combining all these three stresses together, we can find that the combined stresses is only related to the traffic load and the curling stress at day and night. We will ignore the impact from the warping effect. So in the summary, the curling and warping stresses might be added to or subtracted from the loading stresses to obtain the combined stresses. Also, for most of design, we will ignore the impact from the warping stresses. And for the curling stresses, it's actually controversial to include in the design. Usually, we will apply the joints and steels to relieve and take care of the curling stresses. However, when we apply the fatigue principle for the design, it's not practical to combine loading and curling stresses. So it's more important that we will consider the fatigue damage to loading and curling separately and then combine them together. Now we can estimate the rigid pavement responses to the traffic load under different environmental conditions. Basically, there are three typical methods applied for the calculation, including the closed form solution, method of the influence charge, and the finite element methods. In this class, we will only focus on the first one. In this lecture, we will introduce the Westergaard's equations for the estimation of the rigid pavement response. This is actually one closed form solution, and we have some assumptions for the implementation of this equation. First of all, we assume that the PCC slab is very large and it has the full support of the subgrade. In addition, we assume that the subgrade is act as the Winkler springs. Moreover, the slab shall be homogeneous, isotropic, and elastic. Also, it has a uniform cross section. Moreover, we assume that all the force applied on the slab surface are normal to the surface, and we don't have any shear or frictional forces. And the deformation within the element normal to the slab surface can be ignored. Also, the shear deformation are ignored. This equation will actually be applied to measure the impact of the single wear load applied at specific location of the PCC slab. The Westergaard's equations can be applied for three types of loads. The first one is the corner loads, including the concentrated corner load and circular corner loads. In the figure, it shows on the right bottom. The second one is the edge load, which is located at the edge of the PCC slab. And the last one is called the interior load, which is placed in the center of the slab. First, let's consider the concentrated corner load, where the load is applied to the corner of the PCC slab, which is point A in this figure. And then we can estimate the stress applied at the cross-section with the distance of x to the corner. The line A to A prime will have an angle of 45 degrees to the side of the PCC slab. In that sense, the length of the cross-section at the distance x will be 2x. By assuming the thickness of the slab as h, we can find out the cross-section area as 2x times h. For this situation, we can consider the slab as a cantilever beam. In that sense, we can estimate the stress applied at the cross-section with a distance of x as the formula here. We can further simplify this formula as 3 times p divided by h squared. Here you can see that the stress at the cross-section with distance x is actually not related to the distance. This indicates that the stress applied at all the cross-section is constant and is only related to the load applied and the thickness of the PCC slab. The figure here shows a circular corner load applied to the PCC slab, where the load is applied at one corner of the slab. From the figure, you can see that the contact area is in a circle, and the circle is actually tangent to two sides of the slab. The radius of the contact area is defined as A. With this situation, the maximum stress is applied at a cross-section with the distance about 2.38 times square root of A times L to the corner. And of course, the maximum deflection is applied at the corner. In order to find out the value of the maximum stress and deflection, in 1926, Westergaard proposed two equations to estimate the deflection and stresses, which are shown in these two equations. From these two equations, you can see that the stresses and the deflection are all functions of the load applied to the slab, the thickness of the slab, the radius of the contact area, and the letter L as the radius of the relative stiffness. For the deflection, is also a function of the modulus of the subgrade reaction. Well, if we consider a square contact area, then we cannot utilize the Westergaard's equation. In that sense, Alniders proposed a finite element method to find out the new equation for the estimation of the stress and the deflection, which are shown in these two equations. Basically, he introduced one variable c, which is defined as the side length of the square contact area, and c is defined as 1.772 times a. The previous equations relies on one variable, radius of the relative stiffness, and we have already introduced the definition of this value in the previous lecture. Basically, L is a function of the modulus of elasticity thickness of the slab and modulus of the subgrade reaction. Generally, we will only consider the interaction when the distance is less than 5 times L. Now let's check one example for the estimation of the stress and deflection within a circular corner load. The figure below shows a concrete slab subject to a corner load. We know K equal to 100 psi, H is 10 inches, A equal to 6 inches, and the load is 10,000 pounds. In addition, for the concrete slab, we have the modulus of elasticity as 4 times 10 to the power 6 psi, and the Poisson's ratio as 0.15. And we want to find out the maximum stress and deflection due to the corner loading based on the two type of the equations that we proposed in the previous page. For the calculation, we all need to estimate the value of the L, which is the radius of the relative stiffness. We know that L equal to E times h cubed divided by 12 times 1 minus v squared times k to the power of 0.25. In this situation, we have capital E as 4 times 10 to the power 6 times the thickness is 10 inches, and we have 12 times 1 minus 0.15 square times k is 100 to the power of 0.25. With that, we can find out the value of L as 42.97 inches. Then we can find out the value of the stress and the deflection based on the Westergaard's equation. For the stress, we have sigma c equal to 3p divided by h squared times 1 minus a times square root of 2 divided by L to the power of 0.6. In this case, we have the load as 10,000 divided by h squared. H is 10 times 1 minus a is 6 inches divided by L is 42.97 to the power 6.6. With that, we can find out the maximum stress as 186.6 psi. And for the maximum deflection at the corner, we have delta C as P divided by K times L squared times 1.1 minus 0.88 times A square root 2 times divided by L, that is 10,000 divided by 100 times 42.97 square times 1.1 minus 0.88 times 6 square root 2 divided by 42.97, which will give you the result as 0.0502 inches. We can also apply the Arnotter's equations for the estimation of the maximum stress and deflection. To use these equations, we first need to identify the side lengths. C equal to 1.772a, that is 1.772 times 6, which will give you the value as 10.6 inches. With that, we can find out the maximum stress, sigma equal to 3p divided by h squared times 1 minus c over L to the power of 0.72, which give you the value of 3 times 10,000 divided by 10 square times 1 minus 10.6 divided by 42.97 to the power of 0.72, which will give us the result as 190.3 psi. It's actually a little bit higher than the one we calculate based on the Westergaard's equation. That is 186.6 psi. But they are very close. For the maximum deflection, we have delta C equal to P divided by K times L squared times 1.205 times minus 0.69 times C divided by L, which will give us the value as 10,000 divided by 100 times 42.97 square times 1.205 minus 0.69 times 10.6 divided by 42.97. With that, we can find out the deflection as 0.0560, which is also higher than the one we calculate from the Westergaard's equation, 0.0502. So that's the way for us to find out the maximum stress and deflection for the circular corner load. Westergaard also proposed equations for the estimation of the stress and the deflection based on interior load, where the load is applied at the center of the PCC slab. The figure here shows the interior load. The contact area is in a circle within the radius of A, and the load is set as P. With these settings, we can find out the maximum stress by the first equation, where is the function of the load, Poisson's ratio, thickness of the slab, and the radius of the relative stiffness. There's a new variable B, which is a function of the radius and the thickness. B will equal to the square root of 0.6 times a squared plus h squared minus 0.675 times h when a is less than 1.724 h. Otherwise, B is the same to A. We can also apply the second equation for the estimation of the maximum deflection, and similarly it's a function of P, K, L, and A. Generally, the interior load is less critical than the corner load. The reason is like the deflection caused by the interior load is much smaller than the corner load. Now let's check one example for the estimation of the stress and deflection caused by the interior load. Here we will use the same example to the first one, except the load is applied in the interior. For this problem, we need to estimate the maximum stress, which is shown in the equation sigma I equal to 3p times 1 plus mu divided by 2 pi h squared times ln L over B plus 0.6159. In this equation, we know almost all the variables except B. To find out the value of B, we first need to check the condition to compare A with 1.724 h. Here we know A equal to 6, h equal to 10. Then clearly we have a is less than 1.724 h. With that, we can call the equation b equal to square root of 1.6a squared plus h squared minus 0.675 h. And then we can find out the value of b as 5.8 inches. Then we can estimate the value of sigma I by getting the value of p equal to 10,000, mu equal to 0.15, and L equal to 42.97 inches. So we can calculate the value of sigma I as 143.7 psi. The next, we can calculate the maximum deflection sigma I equal to delta I equal to P divided by 8 times KL squared 1 plus 1 over pi times ln A over 2L minus 0.673 times A over L squared. In this equation, we know the values of all the variables. P is 10,000, K is 100, L is 42.97, A is 6 inches. Then we can find out the value of the deflection as 0.0067. By comparing with the first example, you can see that the deflection is much smaller than 0.0502. So that's also the reason we say that the interior load is less important than the corner load. The edge load is defined as the case when the load is applied to one side of the PCC slab. There are two types of the edge loads. The first one is a full circle edge load, where the whole circle of the contact area is within the PCC slab. The second one is a semicircle edge load, where only half of the contact area is located inside the PCC slab. Westergaard also proposed an equation for the estimation of the maximum stress and the deflection for the edge load. The first equation shows the estimation of the maximum stress, and these two coefficients are applied for the full circle scenario. If we consider a semicircle edge load, we have to replace these two coefficients with the two new parameters. And the second equation shows the estimation of the maximum deflection. Similarly, the coefficient 0.82 is for the full circle edge load, and the second one, 0.349, is for the semicircle edge load. At most of the situation, the edge load is more severe. It's actually more severe than both corner and interior loadings. Now let's see another example for the estimation of the maximum stress and deflection caused by the edge load. We will apply the same example to the first one, except the load is applied in the slab edge. And here we will consider the two situations. full circular and semicircular load. First, for the full circular situation, we want to identify the maximum stress, that is sigma E equal to 0.803 times P divided by H squared times 4 times log L divided by A plus 0.666 times A over L minus 0.034. From the assumption, we also have L equal to 42.97 inches, which are calculated in the first example. And by applying the value of P equal to 10,000, H equal to 10 inches, and A equal to 6 inches, we can find out the value of the maximum stress as 279.4 psi. In addition, we can estimate the maximum deflection, delta E equal to 0.431 P times K times L squared times 1 minus 0.82 times A over L. We know K equal to 100 psi. Also, we know the value of L, P, and A. So that gives us the value as 0.0207 inches. And so for the second one, semicircular scenario, we have sigma E equal to 0.803 P divided by H squared times 4 times log L over A. And here we need to replace the coefficient from 0.666 to 0.282 times A over L plus a new coefficient 0.650. That gives you the result as 330.0 psi. For the maximum deflection, sigma E equals to 0.431 divided by K times L squared times 1 minus, here we need to replace the coefficient for the semicircular load, that is 0.349 times A over L. With that, we find that the result as 0.0222 inches. So that's the example for the estimation of the maximum stress and deflection with the edge load. Here we need to pay attention about the coefficients applied for the circular and semicircular load. So that's all about lecture today. Thank you very much for your attention. With that, we have finished all the contents in the stress analysis for the rigid pavement.